Hello and welcome back to Gen Chem with Dr. J. I'm Dr. Janita Pritchett, and on this channel we cover all things Gen Chem related. On this video, I'll be covering the photoelectric effect, and we'll learn how to calculate the energy associated with single photons as well as overall light sources. Let's get started. As I've mentioned in previous videos, this chapter is all about understanding light and how it engages and behaves and interacts with electrons. And so one of the things that was observed as a light was able to interact with different metals is that as that light was hitting the metal surface, the metal would emit electrons whenever it was shined upon that surface. Now, this process is what we now know as the photoelectric effect. Now, a lot of the classical wave theories would attribute this effect to the light energy being transferred to the electron, basically allowing it to then be emitted off of the surface. Now, according to this theory, if the wavelength of light is made stronger, or the light wave's intensity was made stronger, more electrons should be ejected. And remember, the energy of a wave is directly proportional to its amplitude and its wavelength. If there is a dim light used, there would be a lag time before electrons were emitted. So this is what was originally predicted in the theories. Now, we're going to see that this, in fact, was not the case, and we'll learn how we account for this in later calculations. And so shown for you here is just a visual image of what the photoelectric effect looks like, where you have light being hitting a metal surface, and as a result, you see those electrons being emitted. So again, it was originally theorized is that the weaker the light source you would have, there would be less electrons that would be emitted due to this lag time that would exist. Now, of course, there's always a problem with some of our old theories. Well, in experiments with the photoelectric effect, it was observed that there was actually a maximum wavelength for electrons to be emitted. And this is what we know as the threshold frequency. And it was regardless of the intensity of the wave source. We also observed that the short wavelength light, there was no lag time in emitting those electrons. So something had to justify what was being observed versus what was being theorized. And so to solve this problem of why you weren't seeing this lag time occur, we can rely on Einstein and his proposed theory that the light energy was actually being delivered in these atoms as two atoms as packets known as quanta or photons. And so think of these photons as little packets of energy that are delivering energy that could then be transferred to an electron to allow it to emit. Now, the energy of a photon of light is directly related to its frequency, or nu, and it's therefore inversely related to the wavelength. Now, we can calculate this energy associated with the photon through this proportionality constant known as Planck's constant, or the letter H. Now, Planck's constant has a value of 6.626 times 10 to the negative 34 joules times second. And so there's two equations that we can use to calculate how much energy is associated with this little packet of energy or this little photon that is within these different light sources. And we can do that by calculating the frequency times the Planck's constant, or H, which we can also then substitute our light equation into there to expand it to solve this if we only know the wavelength. And then to figure out the total energy for a light source, you would then take the energy associated with a single photon, multiply that by the total number of total number of photons that are found in that light source. So let's try doing a calculation. So here it says calculate the number of photons in a laser pulse with wavelength of 337 nanometers and a total energy of 3.83 millijoules as shown here. Our goal here is to solve for the number of photons. And it's always good to write down the information we know. We see that we have the wavelength, or the lambda, provided for us, and we also know the total energy. Being able to declare what variables you have will help you tease out what equations you should be using to solve this problem. So we saw previously that we had an equation that the energy of the photon is equal to Planck's constant times nu, or we could substitute in our speed of light divided by wavelength based on the information that we know. And so given that we have the wavelength provided, we want to use the second option of the equation shown for us here. Now, in terms of units, our Planck's constant has units of joules times second. Remember, frequency is inverse seconds. Our speed of light is meters per second, and the wavelength is meters. And so we can see that when we're doing this calculation, we would actually have to convert our wavelength value from nanometers to meters to be able to plug in and solve for this problem. So our first step is to take our nanometers provided and get those to meters. And we're using that unit conversion that we discussed way back in chapter 1. So we see that 1 nanometer is 10 to the negative 9 meters. Okay, so if we plug that into our calculator, 337 times 1e to the negative 9 gives us 3.37 times 10 to the negative 2 meters. And then we can plug in and solve for the energy of a photon, where the energy of a photon would equal Planck's constant, which remember is at 6.626 times 10 to the negative 34 joules times seconds. And then we're going to multiply that by the speed of light, and then divide it by our wavelength in meters. Okay, so plug that in. So we have 6.626 to the negative 34 times 3e to the 8th divided by 3.37e to the negative 2. And that gets us 5.89. Sorry, that is incorrect. So when we plug in 337 e to the negative 9, when we plug in 337 times 1e to the negative 9, we end up with 3.37 times 10 to the 1, 2, 3, 4, 5, 6, 7, 10 to the negative 7 as our answer. And so to get our energy of a single photon, we would then take the energy of a photon is equal to Planck's constant, which is 6.626 times 10 to the negative 34 joules times second. And then we would multiply by the speed of light times 10 to the 8th meters per second divided by our 3.37 times 10 to the negative 7 meters. And so we plug that in, 6.626 e to the negative 34 times 3e to the 8th divided by 3.37 e to the negative 7. And we end up with 5.89 times 10 to the negative 19. And in terms of units, well, our seconds cancel here, the meters cancel, and we're left with just our joules. So that's the energy that one photon would have. Now our goal is to figure out, well, what's the total number of photons that are present in something that has a total energy of 3.83 millijoules. And so we'd want to use the fact that the total energy is equal to the number of photons times the energy of a single photon, and rearrange to say that the energy, we'd want to rearrange to say that the number of photons is equal to our total energy divided by the energy of a single photon. But of course, we'd want to make sure that our units align. And you notice that our total energy is in millijoules and our single energy is in joules. So we would need the two to match. And so I'm going to first just convert from millijoules to joules and take my 3.83 times 1 millijoule on the bottom, and 10 to the negative third joules on top. And so that would give us 3.83 times 10 to the negative 3 joules. And so if we plug that 3.83 times 10 to the negative 3 joules into our total and divide by the energy of a single photon, that will give us the total number of photons that we have. So 3.83 e to the negative 3 divided by 5.89 e to the negative 19, and that would give us 6.50 times 10 to the 15 for our total number of photons. Okay, so 6.50 times 10 to the 15 photons are found here. Okay, great. All right, next question. It says, what is the frequency of radiation required to supply 1.0 times 10 to the second joules of energy from 8.5 times 10 to the 27 photons? And so again, we got to understand what we're solving for and what we know. We're looking for the frequency, so that's new. We know our total energy. We also know the number of photons. So stepwise, we would want to go from knowing this information to first figuring out, well, what's the energy of a single photon equal to? And then once we get that, we can then calculate what our frequency would be. And so given the fact that we have the total energy and the number of photons, we could say that the energy of a single photon would be equal to the total energy divided by the number of photons. And so if we plug that in, we have 1.0 times 10 to the second joules divided by 8.5 times 10 to the 27th. So when we plug that in, we have 1 e to the second divided by 8.5 e to the 27. And that gives us an energy for a single photon as 1.17. We would stop after 2 sig figs, but we'll carry the numbers on to 176 times 10 to the negative 26. And this would be joules. So that's how much energy one photon has. And so then when we think about what we're solving for, we know that there's those two equations for the energy of a photon, relating it to the frequency or the speed of light and the wavelength. And so in this case, since we're solving for the frequency, we would want to use this version of the equation, where we can now say that the frequency would be equal to the energy of a photon divided by that Planck's constant. Now we're ready to plug in. We put our 1.176. Again, we're carrying all those numbers through. We'll round at the end. Joules divided by our Planck's constant, which is 6.626 times 10 to the negative 34 joules times second. And so when we do that step, we end up with 1.78 times 10 to the we end up with 1.78 times 10 to the 7th inverse seconds or hertz as our final answer. I hope this video helped you understand about the photoelectric effect and how to calculate the energy associated with photons. Be sure to like, comment, and subscribe, and let me know what additional content you would like to see. See you guys in future videos. Have a great day. Talk to you later.